Alright, this is the energy retest review, and this is to go along with your study guide to help you fill that out. First section is on heating curves, and so first thing that we're going to do is we're just going to label everything. So we need to label the phases. There's 3 phases. There's solid, liquid, gas. Solid is the first phase, lowest temperature, lowest amount of energy, and then liquid. And then the last one is gas. So those are the phases, and then the horizontal lines are going to be your phase changes. So going from solid to liquid, we have melting. And then going from liquid to gas, we have evaporation. And so because those are going up the heating curve and you are adding energy to the substance, these processes would be endothermic. So the 2 phase changes that are in red are endothermic. And then coming down the heating curve, going from gas to liquid, is called condensation. And going from liquid to solid is called freezing. So going up the heating curve are the endothermic phase changes, and going down the heating curve are the exothermic phase changes. Also, there's 2 points on the graph. There's the boiling point and there's the melting or freezing point. So boiling happens, if you think of boiling water, you're taking liquid water and you're evaporating it. So this right here, that top part, that's the boiling point. And so you would find the temperature right here, and that would be your boiling point. So if on the graph, if this was 100 degrees, then your boiling point would be 100 degrees. The melting or freezing point, you go to that phase change. And let's say that's labeled 0, then your melting point or your freezing point. Would be 0 degrees Celsius. The next section are over the 3 types of heat transfer, so conduction, convection, and radiation. Conduction is heat transfer by direct contact or through direct contact. So this is going to be like if you are actually touching something. For example, touching a hot stove, feeling somebody's forehead to see if it feels warm. And so your hand is going to warm up by conduction because you are actually touching something that is warmer. Convection is heat transfer through a liquid or a gas. A lot of times these are going to cause currents. So air currents or water currents, basically circulating air, circulating liquid that warms something up is going to be considered convection. And radiation is heat transfer by electromagnetic waves. Most often the example is going to be the sun. So if you get warmed up by the sun, that is heat transfer through radiation. And so just to draw a little example of these. If you had a bonfire, alright, so this is a fire, and let's say that you are roasting a marshmallow. If you stick your marshmallow into the fire, you would be cooking your marshmallow or heating up your marshmallow by conduction, because you are actually, the marshmallow is in contact with the fire. So that would be conduction. If you decided to roast it from above and you roast your marshmallow, that is through convection, because you are actually taking the heat transfer through the air to warm up your marshmallow. And then radiation is, again, like the sun. So just picture anything dealing with the sun or heating up through the sun is radiation. The next part is the difference between endothermic and exothermic reactions. Endothermic is when energy is put into the system. You could also think of it as energy being absorbed. You could also look at it, that means because energy is absorbed, energy is going to be on the reactant side of the equation. So on reactant side, meaning if you have some compound plus energy equals some products. If you're looking at a graph, endothermic is going to start low and end higher because it is absorbing energy, so it's starting with less energy than it is ending with. Remember, on the right hand side these are your products and the left hand side are your reactants. If you want to think about it, we said the phase changes going up the heating curve are endothermic. So for example, melting, if you have an ice cube and you want to turn it into water, you have to put energy into it. Once you put energy into it, it will melt. So that's why melting is endothermic reaction. Also with endothermic, let me just put some values on here. Let's say this is 20 and this is 10. Your delta H is the difference between products and reactants. So you always take products minus reactants. So in this case it would be 20 minus 10. So it would be, delta H would be 10 kilojoules. And so endothermic always means that it is going to have a positive delta H. Delta H and Q are the same thing, so endothermic also means a positive Q. And then the last thing on the graph is to label activation energy. Activation energy is the difference between the very top and the reactants. And remember, activation energy, or EA, energy of activation, is the amount of energy that is required to get the reaction started. In an exothermic reaction, energy is released from the system. The example that we used of the ice cube melting into water, this would be the opposite. So this would be if you had water and heat energy left the system, it might turn into an ice cube. Also with this, energy is on the product side. So in a reaction, if you had some things that are added together, you would make some more products, and energy would be a product. If we are looking at a graph, exothermic is going to start high and end low. Your delta H is the difference between your products and your reactants. And let's say this is 40 and this is 10. Delta H, the difference, is always your products minus reactants. So it would be 10 for your products minus 40 for your reactants. So it would be negative 30 kilojoules. And so it is negative, that tells you that it is exothermic. So exothermic always has a negative delta H. Also, it would have a negative Q. And then for here, your activation energy is the difference between the top and the reactants, or energy of activation. Alright, the next part is specific heat calculations, where you use the equation Q equals mc delta T. Q is measured in joules, M is measured in grams, C is the specific heat, and that's in joules per gram per degree Celsius, and delta T is change in temperature in degrees Celsius. I also put the triangle here so that it will help us manipulate the equation. So in problem number 1, it says the specific heat of ethanol is 2.46, so that's your C. Find the heat required. So heat required is your Q, or your joules, so that's what we need to solve for. To raise the temperature of 403 grams, so 403 grams is mass, from 29 to 35 degrees Celsius. So we take 39 minus 25 to find the change in temperature. And so then we need to plug it all into our equation. We are solving for Q, so we just need to multiply them all together. Q equals mc delta T, which equals the mass, 403, times the specific heat, 2.46, times the change in temperature, which is 14. Multiply them all together, and the total Q is 13879.3. If we look at what we started with, we should have 2 sig figs, so it would be 14,000. And our unit is joules. The next one, 215 gram sample, so that's telling you your mass. Absorbs 8,610 joules of energy, so joules is your Q. Temperature increases from 35 to 115, so we take 115 minus 35, which is 80. And find the specific heat. So that's what we're solving for. If we look back at our triangle, if you're solving for C, you would take Q over M delta T. So C equals Q over M delta T, which equals 8610 divided by the mass times the change in temperature, so 215 times 80. With 2 sig figs, it would be 0.50. And the unit for specific heat is joules per gram per degree Celsius. Third problem, specific heat of lead is 0.129, so that's your C. Find the amount of heat released, so that's your Q, your joules. When 2.56 grams, that's your mass, is cooled from 37 to 0.2 to 22.5. So negative 14.7 degrees. So since you're solving for Q, you multiply them all together because Q equals mc delta T. So 2.56 times 0.129 times negative 14.7. Your answer would be negative 4.85 with 3 sig figs. And since you're solving for Q, your answer would be joules. For enthalpy calculations, we have to take the total sum of all the products, the values of the products minus the sum of the reactants, and we use the table values for this. So if you're using the balanced equation that I wrote in red, we need the sum of all the products, which are the ones on the right-hand side, and then we subtract the sum of the reactants. So we'll start with just the products. The first product is SiCl4 in a gas, and so if you look over on the table, SiCl4 gas has a value of negative 657.0. Plus, you have another product. You have 2H2O gas, so you have to make sure that you get H2O, the gas, on the table, and it's negative 241.8. But because you have 2 of them, you have to multiply it by 2. You have 2 H2Os. So those are all your products, and then you have to subtract the sum of your reactants. SiO2 solid has a value of negative 910.9. And 4 HCl gas, so you have 4 times the value of HCl gas, which is negative 92.3. So keep your reactants in a bracket and your products and your reactants. So calculate what's inside those brackets first. First one is negative 1140.6. And next one is negative 1280.1. Alright, then you can type in that part. So you would go negative 1140.6 minus negative 1280.1. You should get your answer to be a positive 139.5. And so because it is positive, that tells you that it is endothermic. If your answer was negative, it would be exothermic. The next two sections are just for pre-AP, so if you are not in pre-AP, then you are done. If you are in pre-AP, then continue on. Alright, for the phase diagrams or the butt diagrams, we're just going to label all the different things on here. So this phase right here is solid, and then liquid, and gas. The y-axis is always going to be your pressure, and the x-axis is always going to be your temperature. Phase changes will occur as you cross over the line, so solid to liquid, but the arrow that I just drew would be melting, and liquid to gas would be evaporating. The point where all three lines meet is called the triple point. And that's because all three phases are present. Solid, liquid, and gas. Also for melting point and boiling point, remember you will look at the 1 ATM mark, and you will draw a straight line across. It will intersect your graph at 2 points, right here and right here. The first dot is between solid and liquid, and so the phase change that occurs there is your melting. So that would be your melting point. Could also be called your freezing point. And to figure out the temperature, you would draw that line down. And if my graph was labeled with numbers, you would read the temperature right there. That temperature would be your melting or freezing point. The other point is between liquid and gas phase. And so the phase change that occurs between there is evaporating, which is called your boiling point. And if you wanted the actual temperature of that, you would draw that down and read on your graph, which would be numbered. And whatever temperature is there would be your boiling point. The other thing to point out is this line. Remember, if it has a negative slope, that means that the liquid phase is more dense than the solid phase. An example of something that the solid phase would be more dense than the liquid phase would be a graph that has a positive slope, which would be like that. So positive slope means that your liquid or your solid phase is more dense than liquid. Also, if you had to identify the temperature and atmospheric pressure of your triple point, you would again draw it across to read your temperature or your pressure, which is on the y-axis, and bring it down to read your temperature. The last part is when you have to calculate your Q when it goes through phase changes, and so you have this example is 37-degree water freezes into negative 20-degree ice. So first thing is to draw a quick phase heating curve. And we'll label this 100 and this part 0. So you are going from 37-degree water, so that would be in your liquid phase. So I'll just write right here is where you're starting, 37. And you are going down to ice that is negative 20 degrees. Alright, so this tells you that you are going to need three equations. You need the Q of the liquid, you need the Q of fusion, and you need Q of solid. So first you got to set up each equation. So Q equals mc delta T. Q of your liquid equals mass of the liquid, which I did not give, let's say 10 grams. So 10 grams is your mass. Specific heat of liquid is 4.18. And change in temperature of liquid, you are going to start at 37 and end, start at 37 and end at 0. So right here is your delta T. You're starting at 37, so that's your initial. You're ending at 0, so that's your final. So your delta T would be final minus initial, 0 minus 37. So that's your Q of just your liquid. Then you need your Q of fusion, which is the mass, 10 grams, times the heat of fusion, which is 334, but since we're going down, it's going to be negative 334. And last, you need your Q of your solid, which is your mass, 10 grams. Specific heat of water as a solid is 2.1. And change in temperature of the solid, you are starting at 0 in the solid phase, ending at negative 20. So final minus initial, you're ending at negative 20, so negative 20 is your final, and your initial is 0. Negative 20 minus 0. Alright, so type all these in to get your answers. First one I got negative 1546.6. Second one, negative 3340. Third one, negative 420. So your total Q, those are your Q's for each of the changes. Your total Q, you have to add those all together. And you should get a grand total of negative 5,306.6 joules. So it's negative because it's exothermic. You know it's exothermic because you are going down the heating curve. And you had to add together the Q of the liquid, Q of fusion, and Q of solid to get your total answer.